So we have our first exam a week from Friday. You should try some of these book problems on top of the, this isn't last fall's anymore, it's a couple falls ago. On top of this practice exam. When you take the practice exam, you should be timing yourself. Being constricted to only have 50 minutes is difficult to take an exam, and it's only going to be about 7 questions. So you kind of want to put yourself in that setting by trying this. Keep a clock going so you know how long you spend on each problem. Some problems have multiple parts to it in this particular exam, but you should be prepared to answer any of these questions by the time we're done with the material. I think Monday will be our last amount of new material. We'll do the chain rule on Monday and trig derivatives. I went back and I did a video on the squeeze theorem. So you should look at that. It's possible it could show up on the exam, so we didn't have time for it in class, so I had to skip over it. Instead of coming back to it, I just made a video for it. Last class we covered the definition of the derivative. This link here is the video for that. And we'll finish that today, and we'll start also the section 3.3. So we saw that the definition of the derivative is a limit. Basically, we said that the derivative can be thought of as a function. So we no longer have to do it point by point, like we were doing earlier, where if I wanted to find the derivative at a point, I'd had to use the point x equals a in this formula and take the limit of the secant line to get the tangent line slope. We found out that this formula is more useful, but still it's point by point. And what we'd rather have, if instead of having this where we have to move to another point and do this all over again, we'd rather have a function where we let a essentially be x, let a vary and be just the value x, use that same version of the derivative that had the h in it. And so basically it's the same setup, secant line slopes, taking the limit as the distance between the points goes to 0, and we get the tangent line slope exactly. And so it's a function, and now you give me any x, and I'll be able to spit out the derivative, the slope of the tangent line at that x. I don't have to keep doing it for each individual value of x. And so let's actually see that worked out. You'll know that I want you to go through this when I say find the derivative using the definition. This here is the definition of the derivative. And so let me skip to the next slide, and we'll work it out for two particular functions. I have this function y equals 4x minus 7x squared. We're going to find a shortcut to take the derivative. We shouldn't have to take all this work that we're about to do. But you need to be able to know how to do it, though. And so we go to the definition of the derivative, and we need to work this limit out. We have f of x plus h in the numerator. From that, we are to subtract f of x, and then we are to divide by h. And we're taking the limit as h goes to 0. So we know we're on the right track if by the time we're done simplifying the numerator, everything has an h in it so that we can cancel. We cannot evaluate this limit by plugging in h equals 0. And so, big picture though, this is secant line slope. The limit of the secant line slope is the tangent line slope at any particular value of x, as long as this limit exists. And so this is a polynomial, this is a parabola, it opens down. It has a tangent line slope everywhere for all values of x. It's our job to find the formula for the tangent line slope. Okay, so first up in that formula is f of x plus h. What does that mean? F of x plus h means take every x and replace it with the symbol x plus h. Use parentheses. If you don't, you'll make a mistake. Okay, it's not like you do f of x and add h to it. It's not that. It's every x gets replaced with x plus h. When it comes time to square the x, you'll be squaring the x plus h. When it comes time to multiply the x by 4, you'll be multiplying the x plus h by 4. You'll have to distribute. Okay, let's work it out. How do you square x plus h? You have to take x plus h and multiply it by x plus h. The first terms will give you x squared. You'll get an xh. You'll get an hx. And then you'll get an h squared. But these are the same. We could just put them together and say we have two of them. And so we get 2xh, and then the x squared, and then the h squared. Don't make the mistake of just squaring the x and squaring the h. Don't do that. You'll be forgetting about this middle term. Distribute this across to give you 4x plus 4h. Remember what the goal is. Simplify as much as possible. We are only now working with this part. Okay, so after we're done simplifying it, I guess the next step would be for us to distribute this -7 across. After that point, though, we need to subtract from that just the function f of x. Okay, so we distribute the -7 across. We'll get -7x squared and -14xh and -7h squared. From this, we are to subtract the original function, f of x. You know you're doing it right when these terms that don't have h's in them cancel. I like to do it vertically. Nothing combines in all of the f of x plus h. Nothing combines. When I go to subtract f of x, I'm doing it vertically. So I have, when I'm subtracting the entirety of f of x, I'll have a -4x and a plus 7x squared. And I know I've done it right if I can legitimately cancel those terms that don't have h in them. And you'll be left with the 4h, the -14xh, and the 7h squared. That is your numerator. That's the entirety of the numerator. And we're a few steps away from being done. The hard part is behind us. Questions on this part? Any part in the process gave you trouble? All right. So we divide by h. We can factor out this h. And then we cancel. The whole point is this division by 0 that you have to deal with. And the only way to deal with that is if every term in the numerator also has an h, so you can factor it out and cancel. At this point, you can immediately just plug in h equals 0. You can do it here, or you can rewrite it and then plug it in, whatever it takes. Not x equals 0, h equals 0. And you're left with the function 4 minus 14x. You give me an x, and what this function spits out is the slope of the tangent line at that x. So I don't have to redo this thing for x equals 4, x equals 3, x equals 2. I can now just plug in 4, 3, 2 into this, and it'll spit out tangent line slopes. Okay, we'll find a much faster way to do that. We shouldn't have to go through all that work. So we're going to find a shortcut that will allow us to go directly from the function to the derivative by doing something called the power rule. But we have to wait for that. So how you know? I want you to launch into all of this work. It's when you see, I'll even sometimes do the same thing here. I'll put it in bold for you to emphasize the fact that you can't just use a shortcut. You need to go through the limit definition. Okay. It gets harder the higher the power. And the next example has a square root involved. And that makes it a little more difficult too, the limits with the roots in it. Any questions on this before we go to the next one? All right, so be able to do that. Here's the next one. The function is 1 over the root of x. Okay. Hopefully by the end of the day, we'll do the power rule. We'll be able to get this answer in 5 seconds. You know, what the derivative is. Okay. Unfortunately, though, we're about to spend 5 to 10 minutes working with the definition to figure out what the derivative is. So remember what the function is. F of x is 1 over root x. Here is the formula, of course. the definition of the derivative has the two terms in the numerator, f of x plus h minus f of x, and we divide by h. We take the limit as h goes to 0. So this time, though, you won't have to simplify. I mean, f of x plus h is exactly 1 over the root of x plus h. You can't just, try to separate that root. It is exactly x plus h taking the place of x. Okay, if it was a times in between, maybe you could separate it. Okay, but not with the plus. So from this, we are to subtract f of x. So we just have this symbol in the numerator. 1 over x plus h minus 1 over root x. 1 over the root of x plus h minus 1 over the root of x. That is our numerator. And from that, we are supposed to divide h and take a limit. So here's where we stand. We have to rely on algebra to get us out. Last time it was just sort of multiply it out and cancel. Now we have to do some other things. Now you've been trained, when you see a root, you think the conjugate. But this isn't that, though. We've also seen that when you see fractions on top of fractions, there's a technique of maybe not just putting the numerator fractions together, but finding, yes, the common denominator that would put those numerator fractions together and multiplying both the numerator and the h, the denominator, by that common denominator. That's the technique we're going to employ. These two denominators look a lot alike, right? Root x plus h and root x. It would seem like you would think maybe, it'd be wrong, but you would think maybe the root of x plus h would be the common denominator. It's not that. The product of these two guys is your common denominator. Okay? Root of x plus h times root of x. They're nothing alike. Okay? And so they just look alike. They have nothing in common. So here's what we're going to do. First step, we're going to multiply both numerator and denominator by that product so that we can clear out the fractions. Okay? So root of x times root of x plus h, both numerator and denominator. We're not changing it since we did it to both the numerator and denominator. And what that gives us is what? Let's work it out. When you have 1 over root x plus h and you multiply it by the root x times root x plus h, what does that give you? I'm distributing this across here, and I'm asking, what do I get? The root of x. Thank you. These guys cancel. Guess I worried there for a second. All right, we're good. All right, now we have 1 over root x, and we multiply that by the same thing. And the root x is canceled, and we get root x plus h. Great. Now, be careful. There's a minus sign on that second part of the distribution. So there's a minus sign here. Okay. What makes this so bad is that we have to combine methods. That wasn't enough. We didn't just get left with an h to cancel. We have these two roots now with the minus sign in between. So that one technique wasn't enough. We have to combine this technique with another technique. What? This time the conjugate. So we're going to multiply by the conjugate of the numerator. Also, what I did down here in the denominator, whenever you have the root of something times another root of something else, you can make it one big root. It's not necessary that you do it like that, but that's what I did here. Okay. You could have left it as root x times root x plus h. But please don't try to do things like, now let me think about canceling. Please don't try to think that you can cancel those. No, you can't. Okay. The root, that denominator is underneath both of them. And so it's just not, you can't cancel it. And you'll be going back to where you started at if you try to split it up and to do each one. So this technique of clearing out the fractions is our first algebraic technique. Our second algebraic technique is to multiply by the conjugate. And its denominator is just going to keep expanding. It looks bad, but we're going to have just all these terms in the denominator. Remember that we want to keep the thing that's causing us to divide by 0, we want to keep that separate. So we're not even going to think about considering multiplying out the denominator. We're going to leave it just like it is. We brought in this conjugate so we can multiply out the numerator. Okay, the conjugate is the same thing on the left and right, but with a different sign in between. So that's how we end up with a plus. All right, you ready? Let's work this out. Root x times root x. Just x. The middle terms are going to cancel out. You'll have positive them times each other and minus them times each other. So they'll cancel out. And then we have root x plus h times root x plus h. You just get what's underneath. X plus h. Here's the key though. One of them is positive, the other one's negative. So when you write it out, it's very important that when you write your x plus h, you need to surround it by parentheses and put a negative on the outside. Because if you don't, you'll end up with getting the sign wrong. I mean, you'll get the x's to cancel like they're supposed to, but you'll get a negative. You won't get the negative that you need on the h. So yes, the product of this times this is x plus h, but a negative 1 times a positive 1 is the negative of x plus h. Okay, and just keep all of this denominator in the separate terms. Don't fall for the temptation of trying to multiply that out. It would only make it much worse than it already is. Okay, the whole point, got to keep in mind the big picture. What are you trying to do? You want an h in the numerator. In fact, if there's a bunch of terms, you want them to all have h, because you want to be able to cancel the h in the denominator. It's what's stopping you from finding the limit. It's blocking you. And so, once we distribute this minus across, the x's will cancel out. And we'll have negative h. And we can cancel that negative h with the h from the denominator. And really at this point we can immediately just plug in h equals 0. Just remember that the numerator is not a 1 anymore, it's a negative 1. So numerator is negative 1, h is 0. So I put a 0 in here, and what do I get? I have x times x, so that's x squared, but it's under a root. So it just becomes x. Here I have a root of x and another root of x. And they're added. So there's 2 of them. Okay? And that should be enough, but we'll go ahead one more step and say, if I have root x and I multiply it by x, root x times an x, that's like having x to the 1 times x to the half, where I can add those together and call it x to the 3/2. And I have a 2 down here, and I have a negative 1 up there. That's the final version of the derivative. Now I can take any value of x other than 0 and plug it in here, and it will spit out the tangent line slope. It's a formula that will take input x values and output tangent line slopes. Okay. Once again, that 10 minutes that we just took, we can be able to jump from the function directly to the derivative by the power rule. Okay. What else are on? So I skipped one slide here. Yeah. So what do we use it? We're going to use it for a lot of things. We're going to have a whole chapter of how we use the derivative. One way to think about the derivative is, like we've seen here, it's an average rate of change. That's the secant line slope. And when we take the limit on that, we get the instantaneous rate of change. And then this slide that I had skipped over is us doing it with the business application. I guess let's do it. So we have, I have a cost function, C of x. You give me an x, which amounts to the number of ounces of gold that you want to, the weight, basically, the number of ounces of gold that you're trying to get from a mine, and then the formula that X will be plugged into will be a cost formula, where it'll spit out how much it costs you to mine that much gold. Okay, kind of like a convoluted example, but the point being is that I'm going to make an attempt to explain this with this backdrop of this cost business setup. So what does it mean? What is the derivative? What is it? I mean, we have the formula. We know how to calculate it by the definition. We don't know the shortcut yet, but what is it? What does it mean in this setting? Okay, so it's supposed to stand for a rate of, when you think about a derivative, I want you to think about it as a rate of change. What a derivative is it measures how the function is changing when the input changes. I change the input by some amount. The derivative measures how much the function is going to change by. Okay? It's a ratio. It measures the change in the function divided by the change in the variable, the input variable. That's what a derivative is. Okay? So when I change X, if I want to go from making, having this mine produce some 80 ounces of gold, if I want to switch and change it, make it now produce 100 ounces of gold, I changed X by 20. I'm interested in knowing how much is that going to make my cost go up. As a business, I'm in, that's something I really want to know. I want to make more gold. What's that going to do to my cost? How much will my is it reasonable? Is that something I want to do? Will my cost go up so much that I shouldn't think about this? And so that's what we're doing. That's what this derivative is going to measure. When you have derivative with cost or profit or revenue, these business functions, when you take the derivative on them, then you'll see it in an economics class called marginal. Okay, so the marginal cost. It's the marginal cost of producing so many more units or so many less units. Okay? It's the derivative. It measures the rate of change of the production costs when you change the number of ounces that you're going to produce. Either up or down, doesn't matter. Okay? So if I say that the derivative is some number, I can turn into a fraction and I can interpret it. What kind of units? Well, look at what it measures. It measures how the cost changes when the input changes. So the cost is in dollars and the input is in ounces. So if it's this fraction, then it's going to be dollars per ounce. That's going to be a unit. And it'll give you a number based on the dollars per. If I say it's equal to 17, at a particular X value, we want to say what it means, not just be able to, I don't have the formula in front of me. I don't know, I don't really know how to take the derivative other than the definition. But what does it mean? That's what we want to take out of this slide here. If I say the derivative at 800 is 17, okay, I want you to translate 17 to a fraction. Okay, make it 17 over 1. And go up there and say, okay, so change in cost will be 17 when change in X is 1. That's what it is. The change in cost will be 17 when change in X is 1. What does that mean, though? Change in cost is 17. Is 17 when change in the number of ounces is 1. Currently, you're at 800. You're producing at a level of 800 ounces of gold. Okay? You're getting 800 ounces of gold out of this mine. It has some cost to you. Okay? If you want to go from 800 and change that by 1 to 801, whatever cost you were at, your new cost will go up by 17. That's what this means. When you're producing 800 ounces of gold and you increase to 801, your cost, we don't have any idea what it was, but we can still say and be right that it's going to go up by 17. That extra ounce of gold cost you $17 to mine. Okay? All right, great. So we have some kind of understanding. I mean, it's this backdrop of a business problem, economics, but I just want you to know more than just being able to, use the derivative and later use the shortcut. We really want to know what this derivative means, get our hands on it, like what's behind the scenes, and use it in applications. All right, let's see. All right, as far as slides, I think there's like only maybe one more slide or two here. Yeah, this slide here. These are graphs of functions in blue and graphs of derivatives of those functions in red. So these guys are functions, f of x, and the guys at the bottom are derivatives. So these guys are functions, and then these guys are the derivatives of the functions from above. And our job is to match. All we know is that the derivative represents the slope of the tangent line. That's all we know. The derivative represents the slope of the tangent line. And so as we look at these four functions here, let's consider the slope of the tangent line and what sign it has. That's, we don't really want the value of it. We just want to know what sign it has. We can use that to help us out. Later on, we're going to say, of course, that when the derivative is positive, when the slope of the tangent line is positive, it means something about the function. We'll save that for later, basically. But this is kind of like just from what we know. Let's take these guys and consider what kind of sign your derivative has. In this first function, what kind of sign does your derivative have? Your derivative corresponds to the slope of your tangent line, and I've drawn in a bunch of tangent lines up to a certain point. All of those lines have negative slope up to that point where a horizontal line has zero slope. And basically, you're going to focus on those places where you have horizontal lines. That's very helpful. Places where you have horizontal lines as your slope of your tangent line should correspond to where your derivative is zero. Horizontal line has a zero slope. And that line is the tangent line, so that means that your derivative is zero. What does it mean on a graph? If you're looking at a graph of something and it's equal to zero, it means that it goes through the x-axis, or maybe comes up and touches the x-axis. So whoever one of these four down here should go through zero 2 times. Once on the negative axis and once on the positive axis. It's going to be this guy. Double check the signs on it. It's negative to the left of that. It's positive in between. These are positive sloping lines in between. And then it's negative afterwards. These are all negative lines. And that's exactly what's going on here. If you're looking at a graph and it's supposed to be of a function that's negative, negative means below the x-axis. And positive means above the x-axis. And so, yes, these guys are together. A goes along with Roman numeral 2. These are what we think about. Where it's zero sloping tangent line, that's where you touch the x-axis. Where your negative sloping tangent line, that's where you're below the x-axis. Where your positive sloping tangent line, that is where you are above the x-axis. And we just match them up that way. Okay? So the sign of the slope of the tangent line in A changes from negative to positive to negative. And your graph should go from below to above to below. That's why A goes along with 2. Right, how about B? Now B is special. At the very end of last class, we said that if you have a sharp point, that's a place where your derivative does not exist. We had said that. And so the only one of these that have a place where your derivative doesn't exist at is B. At these 2 sharp points, the derivative does not exist at these points. So down here on the graph, we should see some kind of break. Okay? And another aspect of this is if you have a line, your tangent line has the same slope as that line. It's a constant slope. It doesn't change. As you move from point to point, your tangent line slope will stay the same. That's why this thing is horizontal like this. And then there's some kind of break in it. Then it's horizontal again, and there's some kind of break in it. It's for these reasons that B goes along with Roman numeral 4. It's negative. I mean, it's positive, and all of a sudden it's negative abruptly, and so it jumps down to be negative below the x-axis. Then it should jump back up to be above the x-axis because it abruptly changes again. So that's why B is Roman numeral 4. And now we have to decide between C and D and Roman numeral 1 and Roman numeral 3. Let's use our zero check. Zero tangent line slope. Once, 3 different times. Corresponds to the graph of the derivative going through the x-axis or touching the x-axis. The same amount of times. This guy touches once, while this guy touches 3 times. That's enough, since it's a matching question, to finish it out. I mean, check to make sure the signs work and everything, but yeah, that's enough. So C goes along with Roman numeral 1, and D goes along with Roman numeral 3. And you don't have to really, bother with it too much. Questions on that? I would be able to do something like that. Yes?
Can you go over why the derivative not exists in the graph of the unit?
Oh, okay. It comes from this next slide. That sorry, the previous slide. At the end of last class, we said that we need to be aware of places where your derivative does not exist. The fancy way of saying your derivative not existing is saying that your function is not differentiable. And so we focus on sharp points. These are called cusps or corners. Any place where your function is discontinuous at, you can't have a derivative. And then finally, if you have a tangent line that's basically vertical, then you don't have a derivative there. And so this is the very end of last class. And so this is what we ended up with in that picture. It wasn't a curve meeting a curve at a sharp point. It was a line meeting a line at a sharp point. But the still the idea is that it's a sharp point. So your derivative doesn't exist there. Good question. Anything else? All right. I guess we can ignore this slide. This is something that you could. I don't even know if you have access to this. But anyway, you could play with it and change the function and slide and do things, and you can see the graph below. Anyway, I don't think that's really necessary. So now we'll move on to section 3.3. We don't want to have to use the definition of the derivative every time to find the derivative. We want shortcuts. And so in section 3.3, we learned shortcuts. All right. Take 2 functions, f and g. Make sure you can take the derivative, and let k be a constant. That ends up being a part of the formula. Okay. If I take the derivative of think about this, a constant function, y equals k. Think about the graph of it, and think about what the derivative means. The slope of the tangent line. Okay. For all points on that line, you'll always have a tangent line, which is pretty much the same as the line. And horizontal lines have, what is their slope? 0. So our tangent line here would be 0. So if you have a constant function, y equals 7, the derivative of y equals 7 is 0. Okay? So, fine. What about if you have a line? We saw in the last slide, when we were looking at the matching question, part of the function was a line. But tangent line is supposed to be the tangent line would be actually not just touching at one point. The tangent line would be the same as the line. For all points on that line, the tangent line would be the same as the line. We know that the slope of the line, in this, I'll just call it m. And so if you have a linear function, your tangent line will have the same slope. Also m. Okay? But these are basics. We need more. We need curves. We need how do we deal with polynomials? That's what we really need. And so before we do that, if I take a function and multiply by a number first, and I want to know about the derivative, as long as the function has a derivative, I can just think about that number as like being carried along. I keep the constant and I focus on the function and take the derivative of the function. So you don't have to worry about taking the derivative of a constant in this point. Just leave the constant, carry it down, focus on the function, and take the derivative of the function. Okay, it's this power rule that we'll use to take our derivatives of polynomial terms. So x to an n, and no restrictions on n. As long as it's a real number, it's fine. Okay? And the rule is that you should do the following. Whatever that exponent is, it comes down in front as a multiplier, as a coefficient, and then the new power on x is 1 less. So your derivative will be n x to the n minus 1. Okay? The power rule. So if I had y equals x to the 4th, the derivative, bring the 4 down, take x cubed. To show that by definition, it would take 20 minutes. Because we spend so much time just on squaring when we had a parabola. Imagine if we had it to the 4th power, we'd have to multiply the thing out 4 times. So it would take a lot of time. But now we have this, we'll employ this. You only go into all that work if you see the words by the definition. And I would never ask you for a 4th power to do it by definition. Okay? It isn't last class anymore. It was this class. 1 over root x. That is something that you can represent as x to the n. What's the value of n? What is root x, 1 over root x, represented as, when you write it as x to the n, what's the n? Negative 1/2. Very good. So use the power rule on it. Bring the negative 1/2 in front, and then take away 1 from that exponent to get your new exponent. If you're already at negative 1/2 and you take away 1, you're at negative 3/2. So the derivative would be negative 1/2 times x to the negative 3/2. Okay? And that's exactly what we got. We said it was negative 1 over 2x to the 3/2. We would do it in 5 seconds as opposed to 15 minutes. Question, yes?
When we write our answer, do you want straight plus k at the end? Or no? What do you want?
Oh, you're thinking about going backwards with an antiderivative. You're miles ahead. Stop. We're just taking derivative. Yeah. If you have a derivative and you want to work backwards, then you would add a constant on. If you have two functions added together, f and g, the derivative of the sum is the sum of the derivatives. As long as you can take the derivative on each one. The derivative of a difference is the difference of the derivatives. But the derivative of a product is not the product of the derivatives. Okay? So when we had that function last class, that was this class actually, 4x minus 7x squared. We can put all the rules that we have together, and we can now take this derivative in 5 seconds. Okay, leave the 4, take it piece by piece, term by term. 4x, just like mx plus b, the derivative is 4. Minus 7x squared, keep the constant minus 7. Bring down the 2, and take x to the 1. And you get the same thing that we got, 4 minus 14x. So these derivative formulas are shortcuts, so that you don't have to use the definition. And now you can really appreciate the shortcuts, because we wasted about 25 minutes of class today on those 2 examples. And it took us less than 10 seconds to do both of them. Okay? But the main thing I want you to get is that for the product, it's not the same. Derivative of the product is not the product of the derivatives. Don't do that, unfortunately. I wish I had time to show you why. I mean, it makes sense. Why couldn't it be that? But I wish I had time to show you why. I have to use the definition. But and so here's what it is, though. You do take the derivative of each one, but you do it in turn. Like you do the derivative of the first times the second, and then you leave the first alone and take the derivative of the second. In between those two, you put a plus sign. So derivative of the first times the second plus the first times the derivative of the second. And a plus b is the same as b plus a, so you can rearrange it and be perfectly fine. But when it comes to the quotient, you won't be able to rearrange it because the plus will change to a minus. And so I like to keep it in this order because it's in the same order that the quotient rule has in its numerator. Okay, so let's see an example, an abstract example. I have this function root x, and I have this function g of x, and I'm going to multiply them together to make a new function called f of x. I only have limited information about g of x, though. I don't know everything about g of x. Here's what I know about g of x, though. When I plug a 4 in, I get an 8. When I plug a when I plug a 4 into the derivative, I get a 7. Just from these two pieces of information, that should be enough, actually, to help me find out what's going on with f when I want to find its derivative at 4. Because f is a product, I'll do the product rule. I'll take the derivative of the first, which is that guy. And once you do it enough, I want you to be able to, let me use h. Once you do it enough, I want you to be able to skip this whole step here. But yes, it's x to the half, and you take the derivative, you bring the half down, you take x to the negative 1/2. I want you to get to the point where you can skip right to the simplified version of this. If somebody ever, it comes up so much that you'll just remember it. If somebody ever asks you to take the derivative of the root x, you respond with 1 over 2 root x. And you skip the whole power rule. Because it comes up so often. Okay? Maybe not at first, but eventually I want you to get to the point where it comes up so often that you're able to just skip right through the product rule and get right to the answer. All right, that's half of it, right? Derivative of the first times the second plus the first, and then the symbol for the derivative of the second is just going to be g prime. So there is my derivative on f. If I was to simplify it, I would go with that simplified version here, 1 over 2 root x. And so this is what I'm looking at for f's derivative. It involves g, and it involves g's derivative. So these pieces of information I have, I'm going to use them because I'm interested in f's derivative at 4. So I'm going to plug a 4 in every place I see an x. Okay, every place you see an x, you're going to put a 4 in. So I know that the root of 4 is 2, but I'm just going to, every place I see an x, I'm going to replace it with a 4. So all my x's are now gone, and I have a bunch of 4's in there. And it's my job to answer this question, knowing that g of 4 is 8. Knowing that g prime of 4 is 7. Those are my unknowns, and the rest of this I know. This guy is 2, this guy is 2, 2 times 2 is 4, and I can get the answer, a fourth of 8 times, and then plus the 2 times 7. Or 2 plus 14, which is 60. Okay, so that's the product rule. Okay, and so let's also do the quotient rule. I'll just give it to you. The derivative of the quotient is not the quotient of the derivatives, but the formula you can't be lackadaisical with it, as you could be with the product rule. The order in the numerator really matters because there's a minus sign. Okay, and then the denominator doesn't have a derivative in it at all. The denominator is just the original denominator squared. Okay. You can Google mnemonic songs or memory songs to help you memorize what this is. I just think of top and bottom, and I just walk myself through this every time. First thing I do is the easy part, no derivatives at all, just square the bottom. And then I physically put the bottom in the top without changing it at all. And then I do my action of taking the derivative of the top and having the minus sign, then leaving the top alone and taking the derivative of the bottom. Some low and high, or some low-d high, high-d low, some way to memorize that. Some song or something like that you probably heard of. Anyway, that's the quotient rule. If you have a function divided by another function, as long as there's no division by 0 or anything like that, you could do it. Can we do it? I don't know. What time is it? 45. Okay, yeah, we can do this. 3x plus 1 over x squared plus 1. Use the quotient rule to take the derivative. First thing I do is the easy part of squaring the denominator. Just write it as quantity squared. Don't multiply it out. Then the next thing you do, I physically take that denominator, not the new one, but the old one, and put it in the numerator. And then I take the derivative of the numerator. The numerator is like an mx plus b. Its derivative is m. 3x plus 1 has 3 as its derivative. But then I put a minus sign and I reverse that process where I leave the numerator alone and I multiply it by the derivative of the denominator. Which is what? 2x. Very good. Now, I recommend if they're asking you to evaluate a derivative, which generally that's most of the time, later on we'll be doing things with this as like solving where it's equal to 0, checking the signs on it and everything like that. But right now, we're just evaluating. So my recommendation, don't simplify. Immediately plug in the number of x that they want. Because simplifying is just going to cause a mistake to happen, more likely than not. And so, don't try to simplify. Immediately replace all your x's with 1s. And be careful, there's lots of places to make a mistake. But 1 squared is 1, 1 plus 1 is 2, 3 times 2 is 6. 3 times 1 is 3, 3 plus 1 is 4, 2 times 1 is 2, 4 times 2 is 8. And there's a minus sign in between these two. Denominator, 1 squared plus 1, that's 2, and 2 squared is 4. 6 minus 8, negative 2 over 4 reduces to be negative 1/2. That's your tangent line slope to that function at that particular x value. Negative 1/2, that's a 2, sorry, it doesn't look like it. Okay, that was really fast, I'm sorry. But hopefully you got it. All right, I'll see you on Friday. We'll pick up from here, and we'll head towards the chain rule where we do a function inside of another function. And then trig as well, trig derivatives as well.